All right, logic fans, welcome to our our fifth video, 4.4e, on the meaning of the universal quantifier. And we've been talking about domains of discourse and how they relate to understanding what the universal quantifier means. And so there's one final topic that I should address. And we've said that intuitively the range of objects under discussion is the domain of discourse. And more formally, a domain of discourse is a set of objects. So we've been working with a set of like 3 or 4 objects to make the idea clear. We've specified that the domain of discourse has to be well defined. It has to be absolutely clear what's in there and what's not. And it could possibly have an infinite domain, such as all the positive integers. One final qualification, possibly empty. Okay, so possibly empty. So what we're going to be talking about here are empty domains, all right? So these are kind of a fun topic, and students find some of the behavior of the empty domain with respect to the universal quantifier a bit counterintuitive. Sometimes it's more intuitive once we get to the existential quantifier, but I'm going to cover it here, and it's interesting material. I want to note that we will be dropping and excluding the empty domain from consideration once we get to Chapter 6, which is our study of quantificational syntax. So let's jump into what we mean by the empty domain. All right. So what we're going to do is we're going to symbolize the empty domain with basically this symbol. This symbol here, which is a 0 with a slash through it, to indicate that absolutely nothing exists. So what you're asked to do when you're assuming the empty domain is you're supposed to assume that absolutely nothing exists. Now, what kinds of statements are true and false if absolutely nothing exists? In particular, what kind of universally quantified sentences are true or false if the empty domain is in play? Let's look at some concrete examples. And like I said, this is counterintuitive, but I'm going to try to explain here. So let's take a look at these universally quantified sentences. Of course, you'll note that this one is not a universally quantified sentence. That's a negation. But let's look at these sentences, some of which are universally quantified sentences and all of which involve the universal quantifier. And let's let Fy stand for be a property constant designating the property of being read, okay? And we're going to assume that the empty domain is in play. So if absolutely nothing whatsoever exists, okay? If absolutely nothing exists, is this statement right here the simplest universally quantified statement we can have? Is it true or is it false? Pause now. Okay, hopefully you've had a chance to do it, but this is absolutely a true sentence, okay? Now, this is super counterintuitive, and I know it's like, what is going on now? Now, this is one particular domain. It's a special one, so we're going to cover it in some detail to make sure you're clear on it. But let me try to walk you through the idea here. Let's think about this in ordinary English. So this statement says everything is read. So A here is just everything is read. Now, let me ask you one question. Under what conditions would A be false? So let's just forget about the empty domain. Don't think about that. Just answer this question. Under what conditions would this statement be false? Like, what types of domains would A be false under? Okay, forgetting the empty domain. Okay, hopefully you've had a chance to think about that carefully and slowly. If you haven't, really do pause and think about it, all right? A would be false provided there exists at least one thing, one item in the domain, all right, which is not read, right? So this right here, this is the standard for falsity. Provided this is true, A is false, right? As long as this is not true, A is going to be true. This is the standard for falsity, right? This would be the counterexample to A, all right? Now let me ask you a question. One more question, right? Is that standard for falsity met on the empty domain, right? Is this true if we're on the empty domain? Is it true that there exists, all right, there exists at least one thing which is not read? The answer is no. It is not true that there exists at least one thing which is not read, which satisfies this description. Nothing exists, so nothing's going to satisfy any description, right? And so the standard for falsity is not met, and therefore under bivalence, this is going to count as true, okay? Now, that's really weird, and we're going to work through the others, and it's a very similar line of reasoning for all of them, okay? So let's go ahead and actually do that now. Let's work through B right now. Is B true or false on the empty domain? Pause now. All right, hopefully you've had a chance to work it through, but this is also true for the same reason, okay? The standard of falsity is not met. So B says that, let's go ahead and try it here. Everything in the domain is such that it is not read, or everything in the domain satisfies this description. It's not read, okay? And so under what conditions would that be false? Well, there would have to be at least one thing which is read, okay? So there would have to be at least one thing which is read in order for that to be false. Now, does there exist at least one thing which is read on the empty domain? And the answer to that is no. Therefore, the standard for falsity for that statement is not met, and so it's going to count as true. All right, and I want to draw your attention to something, because you might be looking at both of these and going, God, aren't those contradictions? No, these statements do not contradict each other, okay? So let's take a look at a statement like this. Fy, and for all y, it's not the case that Fy, all right? This is not of the form P and not P, right? P and not P would look like this, like that. Okay, that's what P and not P would look like. Instead, we're looking at a statement like this. It says everything is such that it's read and everything is such that it's not read. There's only one domain on which that is true, and that's the empty domain. That's the only one, all right? And so if we exclude the empty domain from consideration, then these two will contradict one another, okay? But provided we allow the empty domain, this sentence can be true. And it's true when and only when we're working with an empty domain. Okay, so with that in mind, all right, let's go ahead and look at this guy. Is this guy true or false on the empty domain? Okay, well, hopefully you were able to figure it out, because we said that this statement was true. This statement is the negation of this statement. So if this statement is true and this one is the negation, this one is going to be false. All right, so that's going to be absolutely false. This says it's not the case that everything is read, which means there exists at least one thing which is not read, but there doesn't exist anything on the empty domain. So that statement is going to turn out to be false. All right, let's go ahead and look at D here. Go ahead and try this one. I'll give you a chance to pause. Okay, once again, this universally quantified statement is going to be true on the empty domain, all right? It's true because basically the standard for falsity can't be met, right? In order for this to be false, there would have to be at least one thing which was both F and not F, okay? And so that cannot happen on the empty domain. There can't be anything, and so this statement is going to count once again as true. The standard for falsity cannot be met. Let's go ahead and take a look at this particular case here. This is an interesting one. So notice that if you De Morgan's this, right, you would end up with a statement like this. And then, of course, if you were to actually, clean it up a little bit, you would end up with that statement. And we can sort of calm that to just get this. So every y is such that it's F and it's not F. That's going to turn out to also be true, all right, because there's nothing that the standard for falsity is not met once again, right, there's nothing in there that serves as a counterexample, and so that's going to count as true for us on the empty domain, okay? And I know this is bizarre and weird looking, but that's absolutely the case. And so one general lesson you can extrapolate from this is that on the empty domain, any universally quantified sentence is true, okay? However, we have a special concept in logic for this, all right? The special concept is the notion of vacuous truth, all right? So a lot of times, let me just actually define it here. So we'll define it this way. A quantificational sentence, okay, one of the things that we're building up, okay, is vacuously true on a particular domain, for example, the empty domain, provided on that domain the sentence is true and nothing in the domain satisfies the sentence description, okay? So every single one of these that we said was true is actually, in fact, vacuously true, right? These are all vacuous if they're true, right? So first of all, the sentences are true. That's the first condition. But the second condition is that there can't be anything in the domain that actually satisfies their description, okay? So this is an interesting notion. Let me show you a couple of examples here. So let's make sure we're on the same page here, okay? So here's our definition of vacuous truth. These conditions have to hold. And here's a problem for you. So we've got a domain with 3 red cubes and nothing else, okay? And our sort of property constants here are designated as follows: R being red, C being is a cube, and S being is a sphere. And all we're talking about here are these 3 red cubes and nothing else. So my question for you is, for each of these sentences, notice this is not the empty domain, but my question for you is see, the definition of vacuous truth does not require it to be the empty domain. It can apply on other domains. So the idea here is, can you figure out whether these statements are true or false on this domain, and if they're true, are they or are they not vacuously true? Pause now. All right, let's go through these together. So this says everything is red, and if we're talking about 3 red cubes, that's actually true. But is it vacuously true? And the answer is no, it's not vacuously true, because we have this condition here that says in order to be vacuously true, nothing in the domain can satisfy the description. But there are things in the domain that satisfy the description. So it's true, but not vacuously true. Okay, and so hopefully you're seeing why on the empty domain, universally quantified statements are going to be true, but all of them are going to be vacuously true. Let's look at this one. This says everything is such that if it's a sphere, then it's a cube and it's red. Okay, well, this is actually going to turn out to be a true statement, but the big question before us is whether it's vacuous or not. So let's be a little bit careful here and actually jump into this one a little bit. So let's go ahead and take a look at, here's the description in question right here. It's this guy, right? Okay, so here's the description that has to be satisfied. And in order for the statement to be true, all 3 of the objects, let's call the first one A, right? So the first cube, it has to satisfy this description. B has to satisfy this description. And C has to satisfy this description, right? And so the question for us is, are these statements true or false? Well, if A is a sphere, turns out to be false, right? Because A is a cube. We're talking about 3 cubes here. So you've got a false antecedent for all of these. And if you have a false antecedent, every single one of the conditionals is going to be true. So basically what ends up happening is that all 3 of the objects satisfy this description. And nothing can satisfy the description if it's going to be vacuously true. So this is true, but not vacuously true for that reason. Okay, I'm going to spill this on to the next video because I don't want to rush it, and we'll finish the rest of the problems there. So see you on the next one.